we'll get the next time to discuss.
Okay. Yes, thanks everyone for coming, and thanks organizer for inviting me to give a talk. In my talk, I will talk a topic that's not, I feel probably not the core problems in this workshop. It's not about streaming or an problem, but instead it's some problem or some classical problem from like decision making problem. In particular, I'll talk about the problem online, high dimension online calibration. So I think the kind of connection with this workshop is that the algorithm is actually also robust, and actually I think it's even a white box, but also robust. And also I feel the problem, both the setup and algorithm and analysis are all very simple. I hope after the talk we'll get that later. Okay, so first let me talk about the problem, online calibration. So there are two parameters here. One is the outcome space, think of as the alphabet, and also the second is a sequence of key bits. And it's like a sequential decision making problem. So at each state, the algorithm first predict the distribution over the outcome. So the distribution PT is just a distribution over and then after that, the nature reveals the actual outcome, which is one single index. So here the model here is that the adversarial not observes the outcome PT predicted by outcome. Otherwise, is it true that you cannot do anything? But the adversarial can observe anything else. For example, the past prediction and also maybe some internal state of the outcome. That's fine. As long as the final random includes in the kernel observed. Okay, and what does calibration mean? So basically, calibration calibration means the prediction should be close to the empirical distribution. So, or in other words, your prediction PD should be accurate average, and it should hold for every possible prediction. So it's some condition. So more formally, we say an algorithm is absolute calibrated if the following things come. So let me expand the equation in more details. So first we take an average over T, and then the second you take a summation over all possible predictions. And then for each prediction, you look at the days you predict. So for prediction P, look at the days you predict T. And then you can just measure whether your prediction P is close to the real outcome. I'll stop here for a few seconds just to make sure everyone understands. Okay. So maybe let me just explain another way. So basically, you take a summation over all possible predictions you can ever use, and for each prediction, you just look at the days you predict that, and then measure how far is the actual outcome. How far is the average outcome to your prediction, and the average measure in L5, or typically in L1, but you come to this one.
Like, why don't you have to oh, I think this is like two toleration distance, I think.
Sorry.
Like, I was wondering why you don't have to normalize over the possible number of supports.
Actually, you do not normalize it. Because, for example, if every day you use a different prediction, then you average it. Do I ever explain about this definition? I have a very simple example in the last slide. Yeah, but I think it's like important to understand this definition. Okay, so you might have heard of this for calibration in maybe in different areas, and so I also want to mention here, like so the formulation here is about some statistical decision problems. So people call it online calibration, but there are also many other research, for example, offline calibration, where this kind of outcome is not like coming sequentially, but offline, and you want to make sure the predictor, for example, like a neural network, to calculate. And also this in people studying fairness, also fair because it kind of corresponds to group fairness. For people use it for trustworthy, and also in game theory, people also make use of these applications. Okay, cool. So I will give an example here. That's the classical example from the original paper that study online calibration. So as you can see, I put like a weather forecasting figure here, and if you Google, for example, the weather San Diego today, so and whether it's going to rain or not, you actually find that the predictor is it's not like 0, 1, but some probability. So actually there are two. Actually, this probability could have two different meanings depending. I don't know exactly. Depending on which website you use. Sometimes it means, for example, in San Diego, how much fraction of the area are going to rain in this hour. But sometimes it means what's the probability of raining in this area. So I'm taking the data. So okay, in our original paper, they showed this is some kind of fitting scenario. This is because of following. You can think of the weather forecaster as an axis, and at each hour, it's need to predict, okay, what's the probability of raining. So for example, at the first day, first round it's like 1/2, and then after this hour for this day, you see whether it's going to rain or not. So this is what here is sunny. And in the second round, you also make some prediction. Maybe this time you predict 1/3, and then maybe again you observe like the day is sunny. I mean, maybe in the third round you make another prediction and saying the raining probably is 2/3, and you observe raining. And maybe last day you predict 1/2 and you observe. So just as a simple example, so what's the like the average calibration error here? So there are totally 4 days, so you should normalize by 1/4. And then you count the calibration error for each possible prediction. So for 1/2, this is actually perfectly accurate, right? Because you predict 1/2 in the first day and last day. It's actually one day raining and 1 day sunny. Well, for 2/3 and 1/3, actually they have some errors. So for example, when you predict 1/3 of raining, actually sunny, so the error is 1/3, and similar to 2/3. Okay, so now let me just briefly go through some literatures on calibration. I think the original paper is a very classical paper by Fulton and Morat, which is a fundamental result in game theory and also decision making theory. The main result is showing that asymptotic calibration can be achieved. So I think it's a really beautiful and very surprising result. So from a high level, it's based on a reduction to some notion of swap regret. Both the reduction and the designing of swap regret algorithm is very good. So I think it's a very fundamental result. And I think it's also very surprising because here in our formulation, if you first look at it, we don't have any. Well, the algorithm has 0 prior information on actual outcome. So every day the algorithm predict distribution PT and then the outcome. But we make no assumption about this thing. So for example, if you go back to the weather forecasting thing, you will realize that okay, actually the algorithm can be calibrated even if it has 0 knowledge about forecasting weather. Yeah, and actually some history here is that you actually will find like later I'll cite some earlier paper, nice 2 lines, but actually the first paper, the draft actually comes out in 91, but it takes 7 years for a paper to get published in a journal, and it's like sometimes the review at the beginning just does not be resolved until the author like release shortened to 1 or 2 pages. Okay. So I also want to mention that in early 1990s, there follow this work. There are many other calibration algorithms based on different arguments. One is the one by Sergio Hart, which use a min-max argument, which actually I talked about in the last few slides. And people also use like Blackwell or flexibility and many other results. And another thing cool, which is cool here. But I think there's a paper by the enforcer, like the title is just yet another calibrated algorithm. And yeah. Okay. So there are many algorithms for asymptotic calibration, but if you look at all of them, actually you will realize they are really asymptotic in some sense. The reason is that they suffer from the curse of like I just mentioned. So if you look at the rate or like how many days it need to be absolutely calibrated, the number of days they need is actually roughly 2 to the times or exponentially times the polynomial in one atom. So actually the dependence on the dimension is really bad. So I want to say it works well for some special case. For example, if you just consider binary prediction, for example, weather forecasting, you only predict 0 or 1. So that's perfectly fine. But if you move to high dimension, then this is just classical and computer equations. And this high dimensional like outcome space is actually useful. For example, if you want to predict the label of a picture, it is choosing from 1 over 1,000. So you cannot suffer to do the 1,000. Okay, so there's some open problem formulated by some code open question or open problem papers. And basically they just ask, is it possible to get rid of this? And also, interestingly, there are many people studying this notion of calibration, not necessarily online. But in this paper, we can in this recent paper, we can actually see like many people conjecture that this high dimensional calibration is just intractable. In particular due to the standard size of condition plans. I will explain it a little bit. In the next slide. As you can see, like by the title of the talk, so the question addressed by this work is that for polynomial time algorithms for high dimensional calculation. So let me remove this expensive dimension.
Was anything that was exponential time polynomial time? Also, if you like the exponential time, but
sorry. I think maybe polynomial time here is not good. So when I say polynomial time, I really means polynomial number of bits. So it's
okay. So polynomial and D to
yeah. So yeah. Okay, so in the next slide, I will talk about one existing calibration approach, and this approach is kind of simple, and also it illustrates why going from exponential infinity to some polynomial infinity is why people sometimes conjecture is fun. So this is a argument due to Sergio Hart, and this is a min-max argument. So it's not computational efficient. But yeah, and because it's having used some min-max arguments, and probably the runtime of the algorithm is 2 to the t times d or something. And if t is 2 to d, then this is 2 to the t. Okay, but the argument, if you accept a k-lemma, then the argument is very simple. So recall in the previous in the standard formulation of calibration, here I call it the primal thing. So at each step, the algorithm first makes the prediction, so it's a diffusion, and then the nature reveals outcome. So algorithms have nothing, knows nothing about this outcome. Seems very hard, but you can use some min-max argument showing that this primal game is actually equivalent to the dual game. You know, calculation efficiency again. So the dual game is followed. So the nature first commits a diffusion Qt, which is diffusion, and then the Qt is not to the algorithms. Then the algorithms makes the prediction P, and finally the outcome is drawn from this Qt. So in some sense, the nature reveals all the information to the algorithms. So the nature tells the algorithms, I am going to sample from this distribution, and then the algorithm makes the prediction. And this classical paper proved this. These two are actually equivalent if you only care about this statistical or the number of days. So based on this, you can design any algorithms for calibration. So you know the situation.
Example of the same solution.
Yeah, basically yes. So the idea is like, okay, so it's kind of most straightforward thing. You can, okay, since I know this solution, I can just predict that. Right? I can just set PT equal to Qt. Right? So there's some minor caveat, because if Qt is different, then if you just like directly set PT equal to Qt, then the number of prediction you make for every day is different. So you actually count the error for the error just cumulate, because you actually the final error you compute is PT minus IT, something like that. But what you can do is that I can just take an absolute net of the d-dimensional syntax, and then if every day nature told me, okay, it's going to sample from Qt, then I just point in atom that's close to 2 pi. And it's very easy to see that if you use these algorithms, then you can obtain this aforementioned 2 to the d times polynomial algorithms, right? Which is yeah. Okay. And also, it seems like if you look at this example, you realize that okay, maybe getting something better seems to be tricky because here you know, every day if the nature told you what it's going to sample from, then why not just predict from that? You know, if you can get something better, then you must like deliberately not truthfully predict the nature's distribution. So there's some strategy. Yeah. And also, when I say like conditional exponential size, because the absolute method didn't represent like the exponential size. So the main result in this talk is I'm going to give you an algorithm that becomes epsilon calibrated after e to the 1 over epsilon squared days. Then this work against the I think white box fabulous theory. Yeah. Okay. So it means like for if you just take epsilon to be some constant, then you can in this regime you can have some d to the 1 and some poly d or polynomial approximation for this problem. And it turns out that okay, so my algorithm and the first polarized algorithm actually they're good in different regime. For constant epsilon, this algorithm better, but when epsilon are larger, say 1 over pi d, then it's no better whatsoever. And actually, the second result I'm going to mention in this talk is that the best of these two algorithms are actually optimal. So in some sense, you need to either pay exponential dependence on epsilon or exponential dependence on. Okay, I'll discuss about that later. Okay. Okay, so the algorithm is very simple. Hopefully, after I present it, you should you agree with me. And also for me, I feel a little bit surprising. Okay, so just 2 lines for the algorithms. So in the first line, I will just define a base forecaster, which is very naive. So the base forecaster basically just predict average outcome of the last epsilon to the minus I days. Okay. So for every epsilon to the I days, it just uses the last epsilon to the minus I days. And the final forecaster just randomized over them. And here's a more concrete example. Let's say there are 8 days in total, and I'll set epsilon equal to 0.5. Okay, in the first day, you know nothing, so you just predict a uniform random vector. So after the I am describing the forecaster 0 when I equal to 0. So so at the first day, you know nothing, so you just predict some uniform random vector. After the first day, you see the outcome I1 in the first day. So in the second day, the base forecaster just use I1 as a predictor. And then after the second day, it says the outcome measure, which is I2. And then in the third day, it just use I2. And you keep doing it for the base forecaster. And when I equal to 2, the forecaster updates less frequently. Again, for the first day, you know nothing, so just predict some random number. But after the first 2 days, it says I1, I2. Then in the beginning of the second segment, it just predicts the average of I1. And in the third segment, it average of I3, I3 plus I4 over 2. So again, if you move further, consider the forecaster 2, then it's updated less frequently. It will use the last 4 days as the predictor. So initially it's uniform, but after the first 4 days, it just predicts the average. Exactly. Okay. So finally, the total number for forecast I will take is log d over epsilon squared. Yeah. So the total number of days roughly like epsilon to the log d1 or epsilon squared, roughly d to the 1 over epsilon squared. Okay, now I will present an analysis which also are actually very useful. Let me just do a quick warm up. So what would go wrong if you just use one single forecaster? For example, use the one that just use the outcome of the last step. So you can actually here it's very easy to write down the calibration error using some chloroform formula, and which is just the summation of the summation over all days and the difference between prediction at the at day t-1 and at day t, right? Because you always use the outcome of the last day. So I mean the counterexample is very easy. So I mean in every day the nature, because the predictor is always one step behind, so the nature could just at day 1 it shows the outcome is 0, and at day 2 the outcome is 1. So it just keeps shifting. So this error is large. So why having macro-based forecaster would work from RS high level? So you can say like because their counterexample is different, so we kind of hedge the risk. And in the analysis, I will use a potential argument. And here's a little bit more in details. So let's say I will show that if the calibration error is large, then it means this PT should move quite often, or also which means PT are far from their average. And if that happens, then the entropy will decrease level by level. So an entropy will decrease forever. So
The entropy of which one?
entropy of PT. I will talk about this in this slide. Okay. So here I'm just taking a kind of a very a snapshot of the outcome and assume, for example, maybe in the most in for forecaster I, it will predict P1, for forecaster I is prediction is P1, P2, P3 to P1 or epsilon in some time interval. And if you go to one level down, then one level above, then look at forecaster I plus 1. I plus 1 will in this segment will just predict the average we'll just predict the average distribution. And you may realize like in the algorithms there's also other segments and also there's other levels, but so essentially I would zoom in just two adjacent levels. Okay. So let me write down the so from the last slide we know that the calibration error basically for the first for the forecaster here, it's just the summation of PT minus 1 minus P. So basically the change of the predictor. And the first step is just some triangle equality. So this can be bounded by the distance from PT minus 1 to the average, and plus the distance from PT to the average. And then like there's a factor of 2 and some lower order term, because you cannot ignore the first round and take the last round. But that's essentially just the distance from each P1, P2 to P1 epsilon to add to their calculation. And then here's where I use the entropy. So you can prove this. I won't show you in this talk, but you can actually prove this. Like the average distance from PT to their average is bounded by the difference between the entropy term. Yeah, it's not hard. I won't show you in this talk. So basically, so finally we realize that entropy is always between 0 and log p. So if there are log p has 1 over epsilon square levels, then the marginal increase of entropy at each adjacent level is average epsilon square, and if you plug in epsilon square, you realize like average number is epsilon. Okay.
That's the entire group.
Sorry?
That's the entire group.
Basically, yeah. You need to take some type of summation of all like the levels, but I think yes.
So intuitively, what's going on? Like,
so okay, so in theory, okay. So maybe let me explain it in another way. So I think the follow. So if you just analyze the calibration error of the first level, the one that I played most with, the error could be large because the observer the nature could make the outcome like the shift, like changes quite large every days. But you will realize in that case, because it changes quite often, the entropy will cross, so it cannot do it for. For example, the nature could say like at day 1 I play the first coordinate is 1. Then at day 2 the second coordinate, sorry, the outcome is the second one, and 1, 2, 3 to D and 4. So I mean the error for the first level is large, but after that the calibration, sorry, the difference on the entropy is also large, and the entropy is kind of monotone and you cannot change whatever. Yeah.
The entropy of distribution of P.
Yes.
Like QT.
So it's actually not different here because I'll just use PT, but they're all defined by the actual outcome.
This is I actually asked this time.
Good question. I think so. I got entropy set type. I've seen. But also, I think the curve. Okay, I'll talk about lower bound later, but the current lower bound really doesn't match it, so probably you have some aspect, but I think probably not. So you can have also lower bound.
Was there a reason to do like uniform over the sense of something like polynomials?
Oh no, just uniform. Just
Is there a reason why you do uniform instead of like something more?
it's because like
Sorry.
okay, so basically, if we ignore this further, just the difference between entropy, it just sum it up and it's just kind of touched a lot. So yeah. Okay. So just a quick brief note on the outcome. So given outcomes for hypothetical calibration is polynomial for constant epsilon. So actually in my paper in my paper the base forecaster actually predicted the cumulative interpretation instead of just the distribution of the last one. But we can show like analysis similar and found some bigger constant. So I think at last if you use multiple forecasters offering different scale, there are many choice of this prediction. And also the outcome is actually inspired by this classical work of Foster Moran. Actually, I also read in my paper like actually it's kind of inspired instead of using some alpha norm, I use force entropy, which corresponds to the entropy potential here, and also this multi-level things also inspired by my previous work with Aviat and so on. Okay, so finally, I just want to so how many? Okay, sure. I'll just kind of optimality of the algorithms. So as I said, so it's still not that good because it has exponential dependence on epsilon. Well, like the previous algorithm has exponential dependence on D. So in my paper, I actually prove a lower bound, a weaker lower bound. So the lower bound states like you cannot be both polynomial in D and in epsilon. So the number of days need to be at least roughly equal to the log 1 epsilon. So if epsilon is 0.01, then should be some polynomial factor. But later there's a follow-up work by Galway, Richardson, and Binghui there. They actually shows a much better low bound. They show like no algorithm can be calibrated, unless your the number of days your P is greater than some exponential in epsilon or some exponential. Okay, so now like significant improvement. There should be some somewhere. So actually it's a very clever black box reduction to existing lower bound of for swap requirements translation. So actually in the next 2 slides, I will just sketch the lower bound in my original paper. Actually based on some discussion with Adler, we actually realized it's not just give this cosine to the lower bound, also gives lower bound both in one and one in D. So also the sequence is not hard, so I'll just describe my lower bound in this class. But yeah, I think I really like the lower bound in previous paper. In this paper because it's a black box reduction, also very simple. Okay, so just to make things simpler, I will only show you the lower bound when epsilon, one epsilon is much smaller than Q, so think about epsilon as one of log yes. And I'll prove the nano base should be grows exponentially for nano epsilon. So here's the notation. I will divide the coordinates into roughly one epsilon block. So each block roughly has size epsilon d. And here when I write I subscribe B, I denote a uniform random vector on the B block. So it's something like L0, that's one coordinate epsilon. Second unit vector. So here's the sequence. So for the entire sequence, I'll expand the lower bound for the dual game. So the nature will hold you which diffusion I'm going to sample from. So in the hard sequence, for the first coordinate, the diffusion elements always the same. It's just random unit vector I1. But on the second coordinate, the diffusion will be different for the first T over 2 days and the second T over 2 days. For the first T over 2 days, is something like I2 superscript 1. For the second T over 2 days is I2 superscript 2. And you can see like the hard that just grows like a tree. So for the first coordinate, it changes more frequently. For the first 1 or 1/4 fraction, it's something like I311. For the second is I31. So okay. So because we kind of branching a factor of 2 at each level, so eventually the 2 to the 1 base. And at day t, so I'll expand t in binary space. So the distribution of the nature should be something like I1 to 1 and I2 to 1. That's all. Okay, let me give a very high level and maybe through sketch. So we want to prove by induction. And let's define the forecaster to be truthful in the second block. If it's always truthfully predict the set that is I21, I22 during so for example, in the first T over 2 days, its prediction on the second block is always I21. And on the second T over 2 days, its prediction is alpha everything. So kind of divide into 2 cases. If the forecaster is truthful, then the calibration error is kind of additive over these 2 blocks because their second coordinate is different, so their condition are different, and so it's additive. On case 2, if the forecaster is non-truthful and it does not always predict I21 or I22 in the corresponding block, we can argue that there should be some large error on the second. Okay, so this is very maybe an actual analysis could be counted, but actually the sequence is hard than level 4. Okay, I'll just briefly summarize. So I think one obvious question, I think maybe some interesting question too is can you like slightly improve the outline, for example, to d to the 1 alpha squared to d to the 1 alpha. I think our unit part is to fix this, make the house more efficient. So from my point of view, I think the online calibration guarantee seems to be strong, essentially because essentially it makes no prior assumption on the future sequence, but somehow the same algorithms could still guarantee that you can accurately predict the outcome. But at the same time, it's also emphasized a bit some price because it's not that efficient. It's due to the 1 epsilon or extension. But at some point, I'm feeling like at some problem, you can make the dimension small, say not perfect, then probably you can all have some efficient problems. Yeah, thanks, Aaron, for
The dimensional case like t equals 2. do you think your analysis can be improved to get something close? I don't know, like D or something?
Actually, no.
No, okay.
I said because it's a actually this problem. I didn't talk about the outcome by force of around. Actually, I did, so I don't think I can tell. Actually, for Deco 2, there's also some open question. What's the right dependence on one or outside? So I feel maybe the lower one is something like it should be like something like 2.3 or 2.5, but the upper bound is 3 minus 0.01 something like. Yeah, I don't think.
Do you think you can simulate this algorithm in low memory?
It's low memory.
Yeah,
It's log n or s square.
But I guess you need to remember the history, right?
No.
For the first phase predictor.
Okay. So when I
Oh wait, no, it's I guess it's.
you just measure the sum of some time interval.
Oh, I see. Okay, that's nice.
Any other questions?
unless you want to further move it down, it's better.
No, I'm happy with this.
So what do you think actually? Like further move the space down to like.
I so honestly, I don't think like reducing space is the first priority because I think the problem is it still takes a lot of it.
Okay, thank you.